This is the section Inferential Statistics for Econ 307 and Financial Data Modeling. So up to this point, we have been thinking about descriptive statistics. So the descriptive statistics are used to describe the distribution of a variable in a sample. So we looked at a sample of home prices, we looked at a sample of stock returns. That's the sample. And we use descriptive statistics to describe what we're observing in that sample. So the mean, the median, the standard deviation, the variance, skewness, kurtosis, all of those things describe the variable in the sample. That's what we've been doing. The next set of techniques we'll learn are inferential statistics. So this is what we use. This is where we use the information we learn about the sample to find out what might be true about the entire population. So this is the direction that we're going to go, and they're not independent from each other. If you do a good job describing the data, that helps you learn about what might be true in the population. So the descriptive always comes first because we start with the sample mean and the sample standard deviation, and those are the two primary descriptive statistics that we're going to use, or sample statistics that we're going to use to make inference about the population mean. So for example, I'm interested in knowing the average time that a WKU student spends studying. So the population would be all WKU students. The population parameter that I care about is the average number of hours spent studying. But I can't observe all WKU students. I can only observe a sample. So let's say I randomly sample 50 students that I see on campus, and I ask them, how much time per week do you spend studying? That sample will be the basis for my inference. So if everything goes well, if my sample of 50 students is truly random, they represent the population, I can take the sample mean and the sample standard deviation, and I can use that to make inference about what the average amount of time spent studying is for all WKU students. So that's my goal. And there are things that we can do to make the inference more precise, and there are things that lead to imprecise inference. And we'll talk about all of those different things. So the two types of questions we're going to answer with inferential statistics. The first is a confidence interval. So based on what we observe in the sample, what is the range of possible values for the population parameter? So if the population parameter is the number of hours spent studying per week for all WKU students, based on what I observe in my sample of 50 students, what range of values do I think will contain the true population mean, the true mean study hours for WKU students? And we have to generate an interval because we're working with a continuous variable. So I can't say, I think the population parameter, or I think the population mean is 10, because 10 is one out of an infinite number of possible outcomes. What I'm going to do is construct an interval. So I might say, I believe the population parameter, or the average number of hours spent studying per week, is somewhere between 8 and 12. So that's an interval that I think contains the true value. And certain things will make that interval smaller or wider, and we'll think about those a little bit later. Okay. So it's a best guess at the upper and lower bounds. So we're not going to guess a number, we're going to guess an interval. The second thing we're going to do is hypothesis testing. So is there reason to believe a parameter might be equal to some value, and is that supported by the data? So someone might claim the average number of hours spent per week studying is 40. Well, I want to collect some data. I will estimate the sample mean, the sample standard deviation, and based on the sample size that I have, I can either reject the claim that they're making, or I fail to reject the claim that they're making. So we're seeing if the data supports a particular claim that the population parameter is equal to some specific value. Okay. So maybe someone claims that they average 7% a year in their fund. Do we fail or reject do we reject or fail to reject that claim? What you'll see later, we never say they're correct, but we'll either reject what they claim or we'll say there's not enough evidence to say that they're wrong. So a little bit of terminology, and we've been using some of this terminology throughout the course already, but this just formalizes what we mean here now that we're thinking about inference and samples versus the population. So the population is the collection of all subjects. So that would, if the population is WKU, all students at WKU make up the population. So all currently enrolled students, that would be the population. The sample would be the part that we actually observe. So if I randomly select 50 students, those 50 students represent the sample, and we hope that they reflect the underlying population. We'll never observe all WKU students, but we can observe a sample of students if we just walk around and ask people questions. A statistic is an observable value calculated from the sample. The sample mean, sample variance, sample standard deviation, skewness, kurtosis, those are all sample statistics. So that's something that we can actually observe from the sample. I can take the data that I have and I can estimate a number. That number is the statistic. A parameter is that unobserved number that describes the entire population. So I believe there is a number that represents the average number of hours spent studying for WKU students. That number does exist. I don't observe that number. I can only observe the sample statistic, which is the sample mean. So we're going to use the sample, what we learned from the sample, to try to estimate this unobserved population parameter right here. And we're going to think about a couple different ways to do that, some things to think about, and some where you need to be careful, because you can, I'm not going to say you're not going to get yourself in trouble here, but you can do it the wrong way, and you can make claims that are not supported by the data. So we want to think a little bit about a sampling distribution, and this is a little bit different than just taking a sample or just a distribution in the population. It's a little bit different, and it's what forms the basis for our hypothesis testing and our confidence intervals. So I'm not going to spend a lot of time here, but it is important that we think about it a little bit. So a sampling distribution shows the values that a sample statistic can take on and how often it takes on those values. So remember that a distribution is just this set of all possible outcomes and how likely they are to occur. The sampling distribution is the same thing, but it's for a sample statistic. For example, actually jumped it. Let me back up here. What have I done? Okay. So instead of plotting the distribution of x, we're going to plot the distribution of x bar. So the thought experiment that we're going to run here, let's say I have a population. My population is WKU. I could pick one student at a time and plot how much time they spend studying. So I take one student, ask them how much time they spend studying per week, and I write that down. I take another student, ask them how much that time they spend studying, I write that down. And I do this over and over, one student at a time. That's going to give me the distribution of how much time people spend studying at WKU. Instead of doing that, I'm going to take a random sample of, say, 50 students. I'm going to take a random sample of 50 students. I'm going to ask those 50 students how much time they spend studying. I'm going to calculate the average, and I'm going to write that number down. So instead of writing down how much time students spend studying, I'm going to write down the average time spent studying for that sample of 50 students. And I'm going to do that over and over and over and over and over again. So let's say 1,000 times I'm going to take a random set of students and I'm going to find the average amount of time they spend studying, and I'm going to plot that distribution. So instead of plotting the distribution of x, I'm going to plot the distribution of x bar. And the probability distribution for x bar is just f of x bar. So that's the probability distribution. I'm going to show you an example of this in just a few minutes. So this distribution has some properties. It'll have a mean, it'll have a standard deviation. It's very similar to the distribution of some variable x. So I'm going to skip ahead just a little bit and show you what we're thinking about here. So just a quick example of a sampling distribution. So this is a population. So right here, this population is exponentially distributed. So this is, assume that this is the different values of x and how frequently they occur in the population. So what I'm going to do is I'm going to take random samples from this population. So I'm going to take 1,000 samples of size 20, size 100, and size 1,000. So I'm going to take 1,000 samples of size 30. I'm going to find the sample mean of each of those samples, and I'm going to write it down. So this is the distribution of x bar. So notice this is the distribution of x. This is the distribution of x bar. So instead of writing down different values of x, I'm going to take a sample of 30 students, or take a sample of size 30. I'm going to find the average. I'm going to write that down. I'm going to take another sample of size 30, find the average, write it down. And I'm going to do that 1,000 times. And notice that sampling distribution for the sample mean starts to look approximately normal. It starts to look like a normal distribution. So this would be the sampling distribution of the sample mean when the sample size is 30. So that's what we're thinking about with the sampling distribution. I'm going to take samples, find the mean, write it down, do that over and over and over again, and plot that distribution. So that distribution has a mean, it has a standard deviation. So you'll hear me say standard error. So the standard error is just the standard deviation of the sampling distribution. So what's the standard deviation of the x bars instead of the standard deviation of the x's? So the central limit theorem is a very, very powerful result that allows us to use the normal distribution. We're going to use a t-distribution, which is very similar to the normal distribution, to make inference about the population parameter. So the central limit theorem says we can take a sample from any population with mean mu and standard deviation sigma. It doesn't matter what the underlying distribution looks like. In that example we just looked at, the underlying distribution was exponential. If the sample size is sufficiently large, the sampling distribution of the sample mean will be approximately normal with mean mu and standard deviation sigma over square root of n. Mu is the population mean. So in this example right here, the population mean is 3. So this distribution right here has a population mean of 3. Notice when we take the sampling distribution of the sample mean, that distribution also has a mean of 3. That distribution is symmetric around the value 3. And that's what the central limit theorem says. The sampling distribution of the sample mean will have the same mean as the underlying variable, and the standard deviation is sigma over square root of n, which says the standard deviation, the variance, or the amount, or how spread out that those x bars are from mu or around mu, depends on the sample size. So this is what happens when we take a sample of size 30. If we take a sample of size 100, notice it's still centered around 3, but the distribution is now narrower than it is when we took a sample of size 30. So when our sample size increased, the variance decreased. We're observing x bars that are closer on average to the true value. And if we take samples of size 1,000, they're even closer than that. So the central limit theorem is a very, very powerful result, and it tells us we can make inference about the population mean using a normal distribution, and our inference will be more and more precise as our sample sizes get larger and larger. So if we want to estimate a population parameter, we need large samples. If you know what sigma is, which is a big assumption, we actually don't know that in most cases, we can make inferences about the population mean using the normal distribution. So even though we talked about the normal distribution, how to identify when things look normal, when they're not normal, if we're trying to make inference about the population mean, we can do that using the normal distribution even if the underlying distribution isn't normal. And that's a very, very, very powerful result that makes our life a lot easier. So, in our example with asking how much time the average student at Western spends studying, if we want a good estimate of how much time a student at Western spends studying, if we only sample 10 students, we're not going to have a very precise estimate. If we sample 50 students, we'll have a more precise estimate. If we sample 100 students, our estimate will be even more precise. If we sample 1,000 students, it'll be even more precise. So if you're trying to make inference about the population mean of any variable, the precision depends on how large the sample is. It also assumes that the sample is random. Every observation in the population was equally likely to be selected for your sample. All that stuff is still true, but the big thing here is we need large samples. The sampling strategy also needs to be correct with randomness and all of that, but large samples are the main thing we're going to focus on right here. So central limit theorem says if the underlying distribution, even if the underlying distribution isn't normal, the sampling distribution of the sample mean will be approximately normal with the same mean and a standard deviation that gets smaller and smaller as the sample size increases. So how do we use this? Each sampling distribution was centered around 3. That was the underlying mean in the population. That was the center of our sampling distribution. The variance got smaller as n increases. This whole thing gets smaller. So this is the standard error. So the standard error gets smaller as our sample size gets larger. And this is going to directly impact our confidence interval. So you have more confidence in your estimates when your sample size is large. So what happens here, let's say we're going to try to estimate an interval. We might be able to claim, well, it's somewhere between 2 and 3. So again, just send this generic made-up example here. Our inference might suggest, well, it's somewhere between 2 and 3. Well, if we take a sample of, that's when we take a sample size 30. If our sample size is 1,000, we might be able to say, actually, I think it's somewhere between 2.25 and 2.75. So notice that interval is smaller. So the range of values that you can have confidence, a certain amount of confidence in, that you can have more confidence in a smaller interval, or the same level of confidence in a smaller interval when your sample size gets larger. And we'll talk about all of this in more detail later when we actually start looking at this case, a smaller interval that we estimate. If you take one thing away from this slide, it's larger samples lead to more precise estimates of the population mean. More data is better. Right. So now let's think about a confidence interval and the components of a confidence interval and how we actually estimate the confidence interval. So we can apply the central limit theorem, and there's some math behind the scenes here that we're not going to get into right now. So we're just going to look at the result, but again, there is more in-depth analysis we can do that supports this, but I'm just going to give you the actual result. So I've been talking about the normal distribution. We can only use the normal distribution if we know the population standard deviation, sigma. But if we are taking samples, we obviously don't know the population standard deviation. You can't know the population standard deviation without knowing the population mean. Our goal is to estimate the population mean, so we cannot know what sigma is, but that's okay. So we're going to use the t-distribution, which is similar to the standard normal distribution, but it accounts for smaller samples. And as our sample size gets larger and larger, the difference between that t-distribution and normal distribution goes away. So the t-distribution converges to the normal standard normal when the sample size is sufficiently large. So a confidence interval has 2 parts. X bar is going to be what we call the point estimate. So if someone asks you to estimate the population mean or the average number of hours spent studying at WKU, or the average number of hours WKU students spend studying, you're point estimate will be the sample mean. So if you take a sample of 50 students and you get, and someone says, and that sample mean is 10, that's your point estimate. That's going to be the center of the interval. So the interval is going to be centered at whatever your sample mean is, but there's also going to be a margin of error. So this is that plus or minus part. So the margin of error depends on a few things. Alpha is going to be our confidence level, or in this case, actually our significance level, but it's based on the level of confidence. So do we want to be 95%, 99% confident that this interval contains the true mean, 95% confident the interval contains the true mean, 90% confident? N is the sample size. So this t value right here depends on how confident we want to be and how much data we have. S is the sample standard deviation, and N is the sample size. So those are the things that influence how wide the interval is. So if we want to be more confident, we're going to see that the interval gets wider. If we have more data, so N is larger, the interval is going to get narrower. If our sample standard deviation is higher, the interval is going to get wider. So all of these things affect how precise our estimate actually is. And the actual and this comes from the t-distribution, but I'll show you how to calculate that number in Excel. You actually don't have to calculate it. We can actually get that from there's a function we can use that will spit this out. Actually, there's a function we'll use that will give us this entire margin of error. And the actual confidence interval is x bar, the sample mean, plus or minus the margin of error. So we're going to get a lower bound and we're going to have an upper bound. And the confidence interval is just that range of values that's contained in that confidence interval. So we're going to look at estimating a confidence interval. So you will do this using the data in Excel. So I'll give you returns, or I'll give you prices. You'll find the returns, estimate the mean, standard deviation. You'll do it all in Excel. But this is an example where we actually, where I'm giving you the all the pieces of the puzzle. So let's assume we have 126 monthly returns for Tesla. The sample mean is 5.49%, so that's the average return in the sample of 126 monthly returns. And the sample standard deviation is 18.56%. We want to estimate the 99, 95, and 90% confidence intervals for the true monthly return for Tesla. So this is just the return in the sample. This is the standard deviation in the sample. And based on this sample size of 126, we want to construct an interval that we think contains the true value, not the sample mean, the true mean. So for a 99% confidence, our alpha is going to be 1 minus confidence. So alpha in this case would be 1%, but we always use alpha divided by 2. So notice right here, this is alpha over 2. So we're going to take that alpha and we're going to divide it by 2, and that gives us 0.005. Our t alpha over 2 for n minus 1 degrees of freedom is 2.62. I'm going to show you how to get that number later, but for right now, this is the number that we have. So let me see if my document cam will work here, and I'll write out the pieces of the puzzle. So our confidence interval is, I'm going to just do some shorthand here, x bar plus or minus t, but that's t alpha over 2 n minus 1. I just don't want to write that every time, times s over the square root of n. So that is that's the formula for the confidence interval. So this is going to be the sample mean This is our critical t, what we're going to call a critical t value. This is the sample standard deviation. Again, I apologize for my terrible handwriting. And then this is the sample size. So in this problem, we're going to write down all the pieces that we have. Our X bar is 5.49%. Our sample standard deviation is 18.56%. Our sample size is 126. And our t-value that I gave you is 2.62. So I'm just writing down all the pieces that we have. And now we just plug in the values. So our confidence interval for our 99% confidence interval is going to be, so our 99% confidence interval is going to be 5.49% plus or minus 2.62 times 18.56% divided by the square root of 200 and how many observations? I think I wrote down the wrong sample size. 126. I'm not sure where I got to. Oh, I'm sorry. Yeah, right here. 126. So I'm just plugging in the different values for the confidence interval. So the sample mean goes here. The 2.62 is my critical t-value. 18.56 is my sample standard deviation. And then the square root of 126, where that is my sample size. And if we plug all those numbers in and do the math, I'm not going to do it by hand here. I already have the answer. We get 1.16 to 9.82. So we get 1.16, and that would be 1.16% to 9.82%. Right. So this would be the confidence interval, where this 1.16% is 5.49% minus 2.62 times 18.56% divided by the square root of 126. So the X bar minus the margin of error gives you this value here. So this is X bar minus the margin of error. And this upper bound right here is X bar plus the margin of error. So that's how we get the confidence interval. So we would say, based on the sample mean of 5.49%, the sample standard deviation of 18.56%, the sample size of 126, again, this number comes from our confidence level and sample size, I am 99% confident the true monthly return for Tesla falls somewhere between 1.16% and 9.82%. So I'm 99% confident that the true monthly return for Tesla falls somewhere between 1.16% and 9.82%. That's what a confidence interval is. We can't say I'm 99% confident the true mean is 5.49%, because you're 100% wrong if you say that. This just says I'm 99% confident that that interval contains the true monthly mean for the true monthly return for Tesla based on the sample that we have collected. So if we want to change this and we want to estimate the 95% confidence interval, everything stays the same except this t-value. So the t-value is 1.98 for 99%, for 95% confidence. So everything looks the same except this right here. So notice we're using 1.98 instead of 2.62. And our confidence interval is 2.22 to 8.76%. And if we want to be 90% confident, we use a different t-value. It's 1.66. So we use 1.66 instead of the 1.98 or the 2.62. And our interval is 2.57% to 8.23%. So one big thing to notice when you are looking at a confidence interval, and it's important to understand how the level of confidence affects the interval. So if we're looking right here, the level of confidence affects this number right here. The t-value right there is determined by the sample size and the level of confidence. So if our sample size stays the same, our x bar stays the same, our s stays the same, changing the level of confidence will change this t-value. And as your level of confidence goes up, the t-value gets larger. And if the t-value gets larger, you're going to add and subtract a larger number, and your interval is going to get wider. So the more confident you want to be, the wider the interval has to be for the same standard deviation and same sample size. And another way of thinking about that is I am more confident I can hit a big interval than I can a small interval. So if I'm playing basketball and I want to shoot free throws into a standard size basket, I'm going to have a certain amount of confidence. If you make the basket wider, I'm more confident I can hit it. If you make the basket narrower, I'm less confident that I can hit it. And the same thing is true with the confidence interval. If you want to be more confident that your interval contains the true value, you need to produce a larger interval. If you're okay with if you want a small interval, the trade-off is you're going to be less confident in that interval, assuming S, N, and X bar, assuming S and N stay the same. So we're going to do a lot of this in Excel. I wanted to work through one example here by hand, just so you can see where the numbers fit and how we actually get that upper and lower bound. But everything else that we do for confidence intervals will be done in Excel.